All right, here's our first video on heat and heat transfer. Part 1, what is heat? And I'm sure you're saying, I know what heat is. So what is it? What do you think it is? Scientifically, what would you say? So let's get our pen going. Let's use blue. Well, let's use yellow. Why not? So heat, and I'll just give you the scientific explanation of heat. It is the transfer, right? It's a transfer of kinetic energy. That's what it is, basically. And we'll go over more of that. So the transfer of kinetic energy. But there's more to it. It's not only the transfer of kinetic energy, it's the flow of a special type of kinetic energy, the flow of thermal energy. And we'll talk about that. So that's what we're going to be talking about. What is heat? The flow of thermal energy, which is kinetic energy. It's a form of kinetic energy. So just remember, there are two types of energies. It's either kinetic energy, which we'll talk about in a minute, or it could be potential energy. And every other energy falls within these two as subsets, which we will talk about in other videos. So let's clear the board here, and let's get a fresh screen. And let's change the pen. Let's use red. So we said that heat is the flow of kinetic energy, and it's specifically the flow of thermal energy, which is a type of kinetic energy. But what is kinetic energy? What is kinetic energy? Well, kinetic energy is the energy of movement. Everything in the universe moves. Everything is moving. Even when you're sitting still, you're moving. Because what is actually moving? Inside you are atoms, and atoms are moving, right? So we have 7 octillion atoms inside of us. 7 octillion atoms. Let's make 7 octillion here. So here is a million, and we have our billion, trillion, quadrillion, quintillion, sextillion, septillion, octillion. There we go. That's how many atoms are inside you. And all of them are moving. Atoms are always moving. If atoms did not move, so when atoms do not move, and they're always moving, you will get the coldest temperature. The coldest temperature. And the coldest temperature is absolute zero. Absolute zero. And by the way, we have never found absolute zero in the universe. We have never made absolute zero in the laboratory. So when atoms do not move, you will get absolute zero. So when atoms move, that's the energy of movement. The more they move, the more they collide with each other, the more heat is generated, or in this case, thermal energy. So let's clear the page. I'll give you 2 seconds so you can read that. 1, 2, clear the page. Let's say, for example, let's get our pen going again. There it is. So inside, let's just say this is matter, right? And matter is anything that takes up space and has mass. These things would be atoms, let's say. So their atoms are moving within the matter. Now, in a box like this, the atoms are moving slower. So they would have less heat generated, right? So you can see here they're packed and they're moving all over the place and they're bouncing into each other and they're creating heat, because heat is the flow. It's the flow of thermal energy. And again, like I said before, if atoms did not move, then you would have absolute zero. So let's just say what that means. So for example, on, let's say, our little friend Pluto, used to be a planet. On Pluto, the average temperature on Pluto could be negative about 380 degrees Fahrenheit. That's pretty cold, right? And on Makemake, which is a dwarf planet even further out in our solar system, it can get to negative 406 degrees Fahrenheit, generally. Now, absolute zero, remember, absolute zero, when atoms do not move, absolute zero, and I'll write it over here, is negative 459 degrees Fahrenheit. It's actually, if you want to be exact, it's negative 459.57 degrees Fahrenheit. So absolute zero is the coldest anything could be. Now, we don't use Fahrenheit in science. So if we use Celsius, so in Celsius, absolute zero would be, it'd be negative 273.15 degrees Celsius. But we also use something called Kelvin a lot in science. And so in Kelvin, absolute zero is just zero. So 0 degrees Kelvin is absolute zero. So let's review. Kinetic energy. Kinetic energy is the energy of movement. We all move. Everything in the universe moves. The sun moves. You move. Even when you're lying in bed, you're moving because your atoms are moving. Everything is moving. And if it didn't move, if atoms did not move, then you would get absolute zero. All right. So I said before, there are 5 types of kinetic energy, and we're going to stick with thermal energy for now, but let's just write it down. Let's change the pen. This is purple. Why not? You can remember it by the word melts. And we're going to talk about all these types of kinetic energy. So M is mechanical. So we have mechanical energy. When you ride your bike, that's mechanical energy. What do you think E stands for? Little arrow there. Change the pen. Why not? E is electrical. Electrical energy, right? L is light. T is what we're talking about in this unit. It'll be thermal energy. And S is sound. They're all energy, right? So that's how you can remember the types of kinetic energy. And just remember, there's kinetic energy, which is the energy of movement, and then there's potential energy, which is the energy of position. So, for example, if I made a roller coasters are always a good example to make. If I made this roller coaster, here we are. Here you are. You're at Great Adventure or somewhere. The top part of the roller coaster, that's the potential energy that this car has. As it moves down, it has kinetic energy. Actually, this will be potential energy. We'll use PE. Then over here, it'll be half potential energy and half kinetic energy. And at the bottom, it'll be just kinetic energy. And you know, with that kinetic energy, it's going to make the car move up. And we're going to talk about that in later videos also. So for this video, we just talked about what heat was. It's the movement. It's the movement of what? Thermal energy. And it's a type of kinetic energy. One more thing, and I'm going to talk about this more, but if I made say I made a cup of tea. Who wants a nice cup of tea? A cup of Earl Grey. All right, something like that. Here's our tea, and it's very hot. It's hot. So inside the tea, if we just did an arrow inside this tea, here's the liquid, let's say, from the top view. And it's very hot. Why? Because of all the atoms that are smashing into each other. All these atoms are smashing into each other, and they're creating a lot of heat because they're smashing into each other. And again, the heat is flowing out. So there's thermal energy inside your teacup, right? Now, if we compare it to, let's say, a glacier, an iceberg, here's this giant iceberg. And the question is, which one has more thermal energy? The iceberg or the teacup? So remember, if we put our teacup in this picture, you'd hardly even see it. There it is. Let's make it a different color. Make it blue. There it is. There's a tiny little teacup. So you would say, obviously the teacup is hotter. You touch the teacup, you feel the heat because there's a lot of heat flowing. But believe it or not, the iceberg has more thermal energy. It has more thermal energy. The problem, however, is that the atoms are moving slower. And since the iceberg is so big that the atoms do not bump into each other as much. Right? So you have more thermal energy, but the atoms are not bumping into each other as much as in that little tiny cup of tea. And even if they were, you got a bump here, the iceberg is so vast that you're not feeling the flow of that thermal energy, which again is, what is the flow of thermal energy? The flow of thermal energy is heat. All right. So, next video we'll talk more about heat and temperature and more about thermal energy.